Alright guys, we're going to do solution stoichiometry. Alright, so you guys remember when we did just normal stoichiometry, right? Mass stoichiometry where you had an equation, here's your reactants, here's your products. And then they would give you a known mass of A, right? Let's see, it would give you grams of A, and then you would ask you to find grams of C, right? So what you would do is you would start with grams of A, and then you would convert it from grams of A into moles of A, and then you would convert moles of A into moles of C, and then you would convert moles of C into grams of C, right? That easy four-step simple process we've done 1,000 times before. So this was the conversion factor right here. Conversion factor. And then this one also was a conversion. I'll just be lazy. Okay? And then this was your mole ratio, and that's what you started with. Well, in solution stoichiometry, we're not going to be using grams anymore. Okay? So we're going to use milliliters instead. All right? So substitute liters or milliliters in here. Let's say, what if we add liters of A? Right? And then if we still substituted, we still said liters of A into moles of A. Well, what does that look like? Well, that conversion factor, amazingly, is the molarity of A. See how that works? So if you start with a volume and you multiply by your molarity, you have the moles of your substance. The next step is the same. Moles of A to moles of C. Exactly the same. And then the next step is just using molarity again, moles of C, to convert to liters of C. You can do that. But this is the inverse molarity. Okay? See how that is? That's inverted, or the reciprocal. Molarity of C. The inverse of molarity of C. So essentially just focus on canceling your units and you'll be fine. So that's essentially what we're going to do. That's a solution stoichiometry in a nutshell. The same as the mass stoichiometry, except now we're going to use liters. So let's try out just two examples down here. What mass of water will form if 250 milliliters of a 1.5 molar HCl reacts with excess NaOH according to the equation. So we want to know the mass of water. So we won't actually use molarity on that last step. We will use grams instead. So we could still work that way, our way in. Just stick with me. So we start with our volume first. Always try to start with that volume first. It's real helpful. So 250 milliliters. That's good. And then we will then change our milliliters into moles. Hey, I thought you had to use liters, Mr. Russell. Well, there's a cheap way around that. Just put 1,000 milliliters. You'll see me do that a lot. Okay? Saves you from having to write an extra fraction. So 1,000 milliliters into, it was 1.5 molar, right? Of HCl. Sorry, I need to write my units. That's HCl. And so then moles of HCl can convert to moles of H2O. It is a 1-to-1 ratio. Cool. That makes things easy. And now I can just change moles of H2O into grams of H2O just like normal. There are 18 grams of water. So let's see what the calculator says. 250 times 1.5 divided by 1,000 times 18. That will be 6.75 grams of water. Simple enough. Now, this one's pretty much the same. The mass of carbon dioxide produced when 1 gram of calcium carbonate reacts with 2 milliliters of 0.3 molar hydrochloric acid. So first you'll need to write the equation. Calcium carbonate plus hydrochloric acid will react, and this is actually something we'll do in acids and bases, where we'll make this equation, but that's going to make calcium chloride. Those metals switch places, so the hydrogen and the calcium switch places, and it's going to make H2CO3, but it's actually really going to make water and carbon dioxide. So that's an acid-base reaction, and what we have to do is we have to make sure we balance that one. Okay, so we have 1 gram here, and then we have 20 milliliters of a 0.3 molar HCl solution. Now it wants to know the mass of carbon dioxide. Now you should be screaming at the screen right now saying this is a limiting reactant problem. That's because it is. So we first need to find out the number of moles of each one. So that's going to be 1 gram. 1 gram of calcium carbonate. And let's convert grams into moles. The molar mass of calcium carbonate is super easy. It's 100. Let me verify that. Yep, 100. So 1 divided by 100 is 0.01. That's how many moles there are. And then, so now let's find out the moles of HCl. So we now have 20 milliliters, and I can just change milliliters into moles using my molarity. So that's 0.3 moles divided by 1,000 milliliters. 20 times 0.3 divided by 1,000. And so that's going to be 0.006 moles. Divide by their coefficients, so divide by 1, divided by 2. This one is for sure going to be the smallest number, 0.003. Okay, and that's 0.01. All right, so this one's the smallest number, so this one, HCl, is the limiting reactant because this one was HCl. This was HCl. This was CaCO3. That's the smallest one out of these two. So that's the one we're going to use. Now we're going to change it and find the mass of carbon dioxide, which is going to look super similar to the one above it. So we'll then just take, I'm going to do the cheap way. We already found the number of moles right here, right? 0.006 moles of HCl. So I'm going to shorten the step, find 0.006 moles of HCl, because it's a time test, and I'm trying to move as quick as I can. Moles of HCl, and I'll change moles of, changing to moles of CO2. That's right. Well, there are 2 moles of HCl for 1 mole of CO2. And then I'll change moles of CO2 into grams of CO2. And then, and that's going to be 44. So 0.006 times 44 divided by 2 is going to be 0.132 grams of CO2. Excellent. So That one may be real close to one on the test. So you might want to put a star next to that one. One where you would have to write a reaction. Maybe not this reaction because that one's pretty mean. But and then balance it, because if you didn't balance it, you wouldn't get the right answer. And then find the limiting reactant, and then do the last step. Okay? Students who just plunge into this last step are going to usually trip up and lose points. So there's a proper way to do it, and that is it. That's going to be it for solution stoichiometry. We're going to do more when we do titrations, because that's essentially what titrations are.